responsibility
this is Kejin from School of Physical Science and Technology, Guangxi University, China. Thanks a lot to the organizer for giving me the chance to present this talk. This talk merges two works. The first work is resource efficient quantum distribution using integrity silicon photonics. The second work is fully chips basis decoder for polarization encoding quantum distribution. Before jumping into the details, let me give you an idea of our background and motivation. In the past 3 decades, QKD had received wide attention and obtained many achievements all over the world. Particularly, China had launched the first quantum satellites, MISSIS satellites, in 2016, and also reported the first space-to-ground quantum communication network in 2021. With these achievements, QKD systems has gone from tabletop experiments to compact and open systems. Several commercial systems are on sales. However, the voltage of a QKD system is still very large and the cost is also very expensive. If we want to further minimize the size and the cost of QKD systems, a natural way is the use of integrated photonics, which can integrate the optical system into a chips. There are two main platforms, silicon and indium phosphate, for integrating photonic circuits. Several groups use these platforms to realize the chip's basis QKD, such as a demonstration of chip's basis QKD in field, which has been reported by the English group from MIT. They use a silicon photonics platforms. Andrew Sharp's groups from Toshiba report a fully operational quantum communication system, and they use indium phosphate platforms. The goal of our work is to use silicon photonics to build high-speed and low-cost chip-basis QKD systems. This comes with many advantages, such as large-scale integration and material fabrication. Since silicon photonics has a CMOS comparative, it's promising to realize optoelectronic integration of QKD in the future. Our first work is focused on realizing a silicon-based polarization decoder for polarization encoding QKD systems. In previous works, several groups has realized the chips basis polarization encoding systems. Most of them use a polarization encoder chips, and the decoder still use several optical fiber components. To our knowledge, Yang Lin's group from China has reported the first chips basis polarization decoder, but this chips requires of chips polarization controller to compensation the fiber polarization chip. In our first work, we realized a polarization decoder which can analyze the polarization states for BB84 protocol and actively compensate the fiber polarization chips. As shown in the top figure, the main idea of the chips is a polarization to path analyze. When the line are coupled into the chips via spot size converter, we use a polarization splitter rotator converts the horizontal and vertical component of the polarized lines into two paths waveguide. Then the lines on each path was processed by a Mach Center interferometer. The output interferometer constitutes the positive operator where measurements for BB84 protocol. By carefully controlling the phase shift in the ferrometer, the chips can compensate the fiber polarization chips caused by the fiber birefringence. As shown in the right figure, the size of the chips is 1.6 times 1.7 square millimeters, and the chips is packaged with a thermoelectric coolers has a size of 14 times 22 times 9 cubic millimeters. The insertion loss of the chips is 4.6 dB. The rate of polarization compensation is 3 kHz. The average of the intention ratio is 28 dB. Further details of the chips can be found in our recent publication in Chips. In our next work, we design a resource-efficient QKD with integrity chips. As shown in the top figure, in such a system, QKD has a pulse laser chips, an encoder chips for intensity and polarization modulation, bulb a polarization decoder chips, and free-running detectors. All the electronics controlled use a plain circular box. Unlike the conventional QKD systems, the main auxiliary tasks, including the synchronization and polarization compensation, are required to use additional hardware. Our systems implemented this by using states generated by these chips. In the next, we show how to realize such a system. The first work is to realize the required chips. The laser chips based on Indian materials is already mature and commercially available, so we can buy a single frequency laser chips and then assemble with homemade compact plain circular boards. In our previous work, we had realized a polarization encoded chips is integrity and intensity modulator, a polarization modulator, and 3D attenuator. As shown in the left figures, in the classical QKD systems, it's required to use several box optical devices. And in comparisons, our chips only had a size of 4.8 times 3 square millimeters, and the chips is packaged with a thermoelectric coolers. Has a size of 24 times 15 times 5 millimeters. As shown in the right figure, the intensity modulator utilizes a Mach center interferometric structures, and the phase between the two arms are modulated by a carrier depletion modulator. The polarization modulator is realized by an intensity modulator followed by a polarization rotator combiner. Through the experiment testing, we found that the performance of the chips is compared to an advanced box device. Further details of the chips, please refer to our work published in Physical Review X in 2020. As reported in previous, we had realized the polarization decoder chips, so all the chips for the systems had done. To remove the additional hardware for synchronization, we use QB-based fringe distributed synchronization methods, which can synchronize the two remote particles using the quantum states, as shown in the top figure. Unlike the conventional QKD systems, where Alice only encode random bits into the quantum states, and the tie synchronization require additional hardware. In our setups, Alice needs encode the quantum states which are public synchronization streams for synchronization and random bits for key bits distillation. The tie between two consecutive qubits is set by Alice clocks. The encoded quantum states are then set to bulbs with a lossless channel. Bulb receive some of the quantum states and analyze the received qubit, measuring the arrival time using his clock. Then he can take a fast Fourier transform and this square algorithms to estimate accuracy periods. Then he performs the cross-correlation algorithms to calculate the time offset between the two particles. The synchronization is finished by using these published qubits without extreme hardware. This method is inspired by the work of called Randall's work published in Physical Review Applied in 2020. When we finish the tie synchronization process, we can further utilize these published synchronization streams to get a polarization feedback. The process is shown in the right figure. Bob's first estimate the quantum bit error rate using the synchronization bits, checking whether the quantum bit error rate exceeds the preset ratios. If yes, the quantum bit error rate are then put into a feedback algorithms using the greedy distant algorithms for data processing, adjusting the applied voltages of the phase shifts on the decoder chips to feedback the polarization chips. Finally, we perform an experimental test of our chip systems. The results are shown in the bottom figures. The left figures shows the intrinsic quantum bit error rate of our systems. In a 6-hour testing, the total quantum bit error rates for both two bases is 0.5%. This also demonstrates that our time recovery methods using quantum states works well to test the performance of the polarization compensation methods. We continually run the system with a 15 kilometer fiber spoon. We also use a fiber polarization scramble to further mimic the polarization drips in a long fiber spoon. We change the applied voltage of the fiber polarization scramble in step by step with increase 1 voltage every 5 minutes, as shown in the media figures. For 2.4 hour continuous running times, the quantum bit error rates for day and X basis gradually increased to 50% without active polarization feedback. In this stage, with our algorithms, with our polarization feedback algorithms, we are able to compensate the polarization drips and keep a low quantum bit error rate with 1 minute. We then perform a series of 1D QKD experiments with different fiber spoons lengths. As shown in the right figures, we successfully run the QKD up to 115 kilometer fiber with a key rate of approximately 866 bits per second. This is a summary of our talk. We had realized two chip-based QKD device, an encoder which can realize intensity and polarization modulation, and a decoder which can realize the polarization demodulation and polarization chips compensations. Using these chips, we propose a resource-efficient BP84 QKD protocol using integrated chips. Finally, we thank our cooperation, Kejin Wei and Feihu Xu from USTC. The first encoder chip is realized under their supervision. The decoder chip is fabricated by Xiao from National Information Optical Electrics Innovation Center, Wuhan, China. I would like to thank our group member when I work in USTC. And now I went to Guangxi University. I also thank our group members. That's all my talks. Thank you for your attention. This is my email. If you have any question about our work, please contact me.
So thanks a lot. So can you hear us, Kejin?
Yes.
Okay, perfect.
Hello?
Perfect. Very nice.
Yes.
Very nice. So the talk is now open for questions. So maybe I start with one question. So in this photonic devices, especially with the polarization detection and so on, how stable are you concerning temperature drifts, and how do you do you actively deal with that?
Sorry? Can you, sorry?
Okay,
Okay.
I can repeat the question. So, do you act? So, how carefully do you have to control the temperature on those integrated devices in order to have the polarization component stable?
Yeah. You know when I apply the voltage into the silicon into the encoder, how I control the temperature? Yes.
Yeah, yes, whether there's some temperature dependence on the in the integrated photonics for the polarization
Yeah,
control.
we because our encoder chips is packaged with TEC, thermoelectric coolers. When we control the temperature, yeah, we can we can keep the temperature is stable. Yeah.
Okay, okay. So you don't see any negative influence
Yeah.
of that.
Yes.
Okay, okay. So there's some further questions. If not, then oh yeah, there's one. Yeah.
So thank you for the nice presentation. I just had a general question. What are your future ideas of work with this? You showed many different works, and yeah, what do you think the future will give?
Yeah, this is a good question. In the future, we want to record it in our work. We still use a super nano single photon detector. So in the future we want to use a silicon-based detector, such as in gas or silicon detector, single photon detector.
Okay. Thanks a lot. So I don't see any further questions. Then thanks a lot. Oh yeah, there's one question over there.
Hi, thank you for the nice talk. I was wondering if you could tell us, maybe I missed it, but if you could tell us like the rates that you're doing these experiments at, and if you could tell us a little bit about what your limiting factor and the speeds that you're doing this is. Thank you.
Okay. In this work, the rate of our system is 15 megahertz. Actually, we can realize the rate to 1.24 gigahertz. But I know when I work in USTC, I can realize the rates. But now I'm into a new I built a new lab. So this is the first work we realize the rates a little bit low. The limits because the hardware is a little height of the silicon basis encoder. Yeah, maybe when the rate is raising, the hardware is also raising. This may be the limits to reach a very high repetition rate.